personnellement Anaïs, hein, c'est la première fois qu'on se rencontre. Je la remercie chaleureusement pour avoir accepté de venir nous parler de ses travaux. Ce que j'ai pu trouver comme information, tu me corrigeras hein, si tu as besoin de compléter, c'est qu'Anaïs a travaillé sur des grands surveys comme le survey de DES. Elle est impliquée dans la préparation de LSST avec pour objet d'étude les supernovas, mais plus généralement les transients. Qu'on attend très nombreux pour ce genre de survey. Et elle est actuellement en postdoctorat, si je ne me trompe pas, au LPC à Clermont-Ferrand. Et tu avais effectué ta thèse, par contre, ça je ne me souviens plus, c'est au CEA peut-être, c'est ça?
Oui, oui, c'est à Saclay.
À Saclay. Voilà, donc écoute, on va t'écouter parler des méthodes que tu as développées en machine learning, en intelligence artificielle, justement pour les transientes et le time domain. Et merci encore d'être avec nous aujourd'hui.
De rien, je suis très heureuse d'être ici. Et, par contre, je vais changer en anglais.
Bien
Et
sûr.
c'est par l'habitude. Je ne sais pas si vous avez des postdocs internationaux et des étudiants internationaux, mais je
Oui,
suis plus habituée.
on a l'habitude de
Ah,
faire un peu les présentations comme ça en français, en anglais, ça dépend un peu des fois. Et puis après, on passe en anglais en général.
d'accord. Well, so I'll switch to English. I am Anais. I am, as Philippe said, I am a postdoc in Clermont-Ferrand. I did my PhD in Saclay and a postdoc in Australia at the ANU with Brian Schmidt. And today I'm going to tell you about machine learning in time domain astronomy and supernova cosmology. So I'm going to take you through two things, like two little parts, two different parts of my presentation. The first one, I'm going to talk a little bit more on focus on some types of transients and then go towards the future with LSST, which is a broader scope. So when we think about the transient sky, we don't really think about the transient sky much unless you work in one of these fields, actually. So you have things like variable stars or exploding stars like supernova here to the top right that basically can outshine a whole galaxy of millions of stars. And then a lot of people have been talking about the kilonova, which is in the bottom left, two neutron star mergers, two neutron stars merge and they produce a kilonova. So that's something that is changing in the sky. And then you have a bunch of other types of phenomena like AGNs, TDEs, which are tidal disruption events. Actually, an asteroid is also known as a transient object because when you take an image and you take a second one, it has change magnitude. So all this is part of what we call the transient sky. Now, how do you detect transients? The 101 in a nutshell is basically you take an image, let's say for last night, that's the observation on the top left. Then you compare it to a template. It can be depending on the transient that you're searching for. It's a year old, or it can be a stack of images, or it can be something different. And then you do a subtraction, what we call a difference imaging, and you find everything that is transient in the sky. Not only that, you find a lot of bogus things because, as you all know, astronomical images have their particularities, and the subtraction sometimes can go wrong. I'm not going to enter into why they go wrong, but I think it's important to know that there's a lot of spurious detections of transients in surveys. Now, I'm going to talk about another thing apart from images, which is called light curves. Basically, light curves is observed luminosity either by difference imaging or C modeling photometry or false photometry or whatever photometry you want to do. But it's basically the monitoring of the change of the brightness of the object through time. So this is a light curve. Here I'm showing you one from a supernova. And some of the objects have very characteristic light curves in the sky. So for example, supernova, AGNs are a little bit more complicated, but our Lyra are quite well known, etc. Okay, so I'm going to come back to this concept of light curves a lot. So that's why I wanted to remind you this. Now, I'm going to tell you about two things. One is kind of the present, although the dark energy survey has stopped taking images already. And then I'm going to go through to the future. And I'm going to center the present for the supernova survey in the dark energy survey. And for the Veracity Rubin Observatory, I'm going to center a little bit wider in everything that is transient, okay? Now, let's talk about supernova, and in particular, type 1a supernova. So, supernova are very luminous stellar explosions, as I showed you just before with a little video, but they have different types. So you have type 1a's, which are the most well-known ones, that are thermonuclear, and then you have type 2's, 1b's, 1c's, and a zoo basically of other types. And some types are actually transitionary types, but that's astrophysical studies. But when we do cosmology, we search for type 1a supernova mainly, because type 1a supernova have a property that is, if you see on the top right, you can see that that's a light curve of different type 1a supernova. And if you actually put into a standard schema, which is basically using the equation on the left, basically parameterizing through its stretch, which is basically kind of the width of the light curve, and its color, you can actually put them in the same frame. What does this mean? It basically means that we know how bright they shine, and therefore we can compute their distances, which is very useful in cosmology, because to measure distances, to measure redshifts, we know how it works. It's basically taking a spectra, for example, and seeing the shift to the red or the blue if you're looking at close by objects. But for the distances, you need something that you know their brightness, or you can standardize their brightness so you can measure distances. So it's like putting light bulbs or candles around the universe and using it to measure distances. So that's why everybody talks about type 1a supernova. They're very standardizable, and we have used them for the last 20 years to measure distances. So we know very well how they work. So the Dark Energy Survey, it was a survey that lasted 5 to 6 years, depending which mode you see it. It was a survey dedicated to doing imaging of the sky, based on the Blanco telescope, which I'm showing here to the left. And you can see the footprint of the Dark Energy Survey to the right, which is like a tank, a red tank. The tank was not on purpose, it was because they were trying to overlap with some very well-known fields in the sky. Some of them you may know them. But what I'm going to talk about is not about the whole survey. I'm going to talk about a little part of a survey, which is the supernova survey. So DES had 4 primary probes, galaxy clusters, weak lensing, large-scale structure, and type 1a supernova. And the survey for time domain supernova, which is the time domain survey, was only in the little circles I'm showing in blue or red. So these are deep fields. And what we did is that we pointed the telescope there with a kind of a good cadence, which has multiple visits in GRI set during the 5 years, to try to map this transient sky, this time domain. So the bottom line is that we should have around 2,000 type 1a supernova from in these images. And with that, we want to do cosmology, okay? So to give you an idea of the quality of images from the ES, this is an image of an NGC 253, and this is an image, of course, from the ES. But what we're trying to find the supernova is not in that beautiful close by galaxy. We're trying to find supernova that is exploding here to the bottom right and then very far away galaxy. So basically our photometry is tricky, and detection is also tricky. Now, Blanco gives us, and DCAM gives us the photometry, so we can construct the light curves. Now, how do we do our analysis? So we take the light curves that you see on the bottom right for an object, and you have the monitor of the brightness against time in different filters. Now, I have told you that supernova come in different types. So OSDES, which I also belong to, which is the Australian counterpart of the Dark Energy Survey, was in charge of doing the spectroscopy for DES. What we did was we took the AAT telescope, the Anglo-Australian telescope, the instrument 2DF, which has almost 400 fibers, and you can put those fibers and get the spectra in 2.1 degrees, which is basically the field of view of DCAM. and get spectra from galaxies and transients. So on the bottom left, I'm showing you an image of a DCAM, so all the black CCDs. And then you can see in orange the field of view of 2DF. And in little orange points is the fibers where we put them. So also these not only real-time supernova typing, because we get spectra for typing the supernova, but we also get the redshifts for the supernova from the host galaxy. Okay. But of course, if you know how spectroscopy works, it requires a lot of time. You actually, because we're in time domain, you need to get the spectra in a time window that is very small. So when we classify with the spectroscopy, we have some challenges. And this is where all the machine learning parts will come from, is we're trying to classify things, and these are type 1a supernova, which varies, and this is minus 14 days of peaks, and then we're going to the peak magnitude, and then we're going after a peak magnitude. You can see how the spectra changes. So not only it changes, which makes difficult the classification, you need the time window. You actually have a lot of biases in the selection because you cannot have a complete sample. But that's what we use usually in cosmology. So that's what you usually know when you talk about cosmology results with type 1a supernova. So in DES, we published last year or the year before, I cannot recall which one is anymore, the first 3 years results with a sample of type 1a supernova only classified with spectroscopy. Now, this is where the machine learning part comes by, because we know we have biased samples. Spectra is expensive, so why cannot we use these likers to classify the supernova? So to do that, there are different methods. I am not the only one that has worked on this to classify supernova in different subtypes. But I developed a code called supernova, which is basically RNNs in different flavors, LSTM, GRU, that can allow you to classify these likers at any point of time, which is something interesting when you think about it, especially for the future, because we want to probably know that this is a type 1a supernova before it has faded out. And this is what is shown to the right. You can see a light curve, and then you can see the evolution of the classification probability with time. And in red is the probability of being a type 1a, and in yellow is a probability of being non-1a, okay? So in these very traditional RNNs, I'm gonna tell you results with DES, but then I'm gonna tell you a little bit more about Bayesian neural networks, which I think are very promising for the second part of the seminar. So the power of supernova is that it's actually quite fast, and that's a good thing about the machine learning algorithms. Once you train it, they're pretty fast to implement. You can classify thousands of likers per second, and you can apply it to data that has been taken 5 years ago, which allows us to exploit much more the DES data. So what I'm going to show you here is these are the deep fields of DES. So on the top, you see S1, S2 field. So those are two fields. In red are the ones with the 3-year sample. So these are spectroscopically confirmed. In blue, it's the ones that we are classifying with machine learning. And then you can see the other fields the same. And I'm going to do like a time lapse. Like if you were live in that survey, classifying supernova, how many would you get? So you can already start seeing the type 1a supernova using photometric classification. The density is amazing. Like the number of supernova that we can classify as type 1a compared to the number that you can classify spectroscopically is orders of magnitudes higher. Okay, so that's what we did. We took supernova, we trained it, we classified the sample, and we're actually doing our cosmology analysis right now for that. But to give you a hint of the power of this, I wanted to show you a Hubble diagram, and this is completely preliminary. The axes are blinded, so you cannot read any dark energy constraints really from it. So on the left is the Hubble diagram with around 2000 type 1a supernova. And on the right, you can see the contours for omega matter against W, which is the equation of state of dark energy. And you can see the difference between the 3-year contours, which are in red, against the 5-year contours. And you can see already that our analysis is becoming more accurate, not only because of photometric classification, which allows you to study the populations better, gives you less selection bias, etc., but also because we are doing a lot of work of precision behind it. But because this is a talk about machine learning and not about cosmology constraints, I just wanted to show you a little bit what's the impact of all these machine learning algorithms into something as precise as cosmology. And now I'm going to search towards the future because I think that's where a lot of developments are happening. And I think it's very interesting for the machine learning community to see forward in the next 10 years what's going to happen. So what's coming in the next 10 years for optical astronomers like me is we have the Rubin Observatory Legacy Survey of Space and Time. It's a huge survey with a huge telescope at 6.7 meter equivalent with the world's largest CCD camera. The field of view, you can see it on the top right with a full moon to scale is that large, which means every time LSST takes an image of the southern sky, it will cover a huge area with a depth that we haven't seen in optical astronomy before. So right now, CTF would see around 21.5 magnitudes. DES, we went deeper, but these were little fields. But LSST we can go, well, depending on the observing strategy, can go 23 magnitudes, which is pretty amazing. So it's a 10-year survey. I actually should correct this. We just received word that we are starting a little bit later because of the COVID situation. We are delaying 1 year the start of LSST. But the whole point is that we will get 1,000 images per night, which is around 15 terabytes per night, which means 10 million transient candidates per night. So if you're not a radio astronomer, you will be shocked by this amount of data because the radio astronomers are very used to large quantity of data, and that's why they do hardware cuts to their triggers. But for optical astronomy, this is like, you cannot believe it. So LSST will provide, of course, there is proprietary data, and now the people that are in INSU are part of LSST as well. Not everybody, but you have PIs as well in LSST, which is great. But apart from the proprietary data, which we will have a copy here in the CCI and the Observatoire in Lyon, there is a public stream which comes from a different image analysis. What I told you, this subtraction of a new image against an old image, and that light curve with that difference image analysis. So this will be public. It's the LSST public alert stream, but with 10 million transients per night, which means how do you go from that many alerts to actually getting your science done? And that's where the little fish comes in. So you have this huge quantity of data. How do you get these fast transients, variable stars, AGN? How do you coordinate multi-wavelength and multi-messenger follow-up? How do you connect all data from different surveys? So that's where Think comes by. Think is a broker that was born in France. It's designed for LSST. Think is part of we are actually bidding to become one of the LSST official brokers. There will be a handful of them. Think is the only one French. There's a couple in Europe, some in the US, and for example, one in Chile as well. And we're getting towards the official selection. We already sent everything. And we hope to become one of the official LSST brokers. So for the machine learning part, I'm going to tell you about how do we do time domain astronomy with machine learning in Think. So first of all, it's a community-driven effort. So if you're interested, you have a science case that you would like to explore, Remember, this is public data, and right now we are deploying with CTF, for example. You can come in and join us and work to get your science out. But it's also very robust for this LSST alert stream, which has such a large volume. So it's led by myself, Julien Peloton in IGC Lab, and Emily Ishida as well in Clermont-Ferrand. And the idea is to do everything. If we can, we want to do all the science we can in time domain. So I'm not going to tell you about all the details of how Think works. Basically, you have LSST alerts. We have a bunch of models like cross-matching of surveys, machine learning classification, filtering, so you can get something smaller for your science in different ways through a science portal, through an API. But I'm going to tell you about the machine learning part. Okay. So ML is great because it's ideal for large data volumes. It's fast. It can help you to identify known transients. For example, if you have a supervised learning, you can train it to classify things. But it can also help you to classify unknown transients, like with isolation forests and finding anomalies and things like that. I think the challenges are that we know that we don't have training sets that are representative. We don't know everything that is in the universe and in the sky. And also, if we want to do precision science, how do we get a bias-free or something that has meaningful uncertainties to do precision analysis? So I'm going to talk about the challenges more than the benefits. So the first one is representativity. We know that what we really know in the sky is very small sets. It's the sets that we have built doing spectroscopic follow-up, multi-wavelength analysis, very complicated analysis to understand what's going on. So most of these training sets are, for example, for supernova are thousands. It's not that large. And overall, they are biased. They don't contain the whole reality. They may target just a subpopulation of the whole transient world. And what we do is usually we use simulations for training and benchmarking. So um, that can pose some problems. So for example, let's say you have a simulation and you simulate the peak brightness of a supernova in I, okay? You use this distribution, which is pretty simple, but it's easy to model. You train your classification algorithm. Now, you use that classification algorithm to apply it to data, which may have the same range of peak brightness in I, for example, but maybe the distribution is a little bit different. So when you classify, you may find some things like accuracy decreases. And this is something that some people have seen in their studies. If you don't have a representative training set, your accuracy of classification will be decreased, which means you cannot trust completely what the classifier is providing you. Now, oh, I got, yes. So you can do this. So what you can do in this case will be to try to improve your training set. So how do you improve your training set? Well, either you try to go to understand this distribution or go to the tails of the distribution or something like that. Well, one of the things that we're exploring is using active learning. So what's the idea behind active learning? It's basically you have a label pool on the left, which is your training set, and this comes from data actually. You train your machine learning model. You apply it on a label pool, which is the objects that you have new that you don't like, they're right now in the sky and you don't know what they are. And instead of like breaking there and saying this is a 50% probability of being an Auroral Lyra or this is a 70% probability of being a kilonova, you evaluate this classification into which object should be better to get an understanding what it is to improve your machine learning algorithm. So you're basically putting in the loop an annotator, which in our case is a mixture of a machine, which is the telescope that you're pointing to this object, and a pipeline to reduce the spectra and decide what it is, and a human that probably verifies it. So this is a loop where you can actually choose your follow-up to improve the machine learning algorithm to improve the training sets. And I think this is pretty interesting, especially for LST, because we are in this whole new era of data volumes. So we will have so many events to classify. How do you choose them? So what is the advantage of this active learning against anything else? So here I'm showing an accuracy evolution against the survey duration. So we are supposing that you start with a sample that is quite small of known objects. And over time, you do this loop to actually improve your training set, okay? Now, in red and yellow, there are two ways of doing the choosing a little bit randomly. It's a like choosing in a passive mode. And in blue, you can see the active learning strategy. If you put this loop inside the choosing of the follow-up. And you can see that the accuracy increases much faster than the other two methods. So this is actually quite interesting. And for LSST, this is exactly what we want. We know we will find the things that we don't know what they are. Not only those are the anomalies that are interesting, but we want to improve our training set so we can classify better the things that we are interested on. So that's exactly what we're doing in Think. We are putting that active learning loop inside the broker. That's a work led by Marco Leoni, and of course, Emily Ishida, Julien, etc. And we are also doing it for cosmology. So this is a coin and LSST desk project called Respect. We already have a publication online and there's a second one coming up. So you can see two different approaches. Think is more general, transient time domain, while Respect is really about supernova cosmology. And you can see how these active learning methods can help to have a better classification for the future. The second part I wanted to tell you is about meaningful uncertainties. So we want to do scientific analysis. So what is a robust method in machine learning for us? It's one that you can trust the probability. If it tells you 90% certainty there is a kilonova, you will get it, or 90% that is I don't know, a counterpart of a fast radio burst or a GRB. But what do you mean about meaningful uncertainties as well for statistical analysis? So I love to show this. This is like a mock. I use make moon in scikit-learn to show the idea. Let's say you have a training set. Okay, so these are the two moons, the blue moon and the red moon. Okay, and you train your classifier, your machine learning classifier, and you evaluate it with different data sets. Okay, they all come from moon. So this is a moon as well with the same kind of noise. You can see the classification is pretty good. Most of them are in their good sides, but I circle in blue and red with the borders, the ones that got misclassified, okay? Now, this is pretty good, but if you start increasing the noise, like the distributions of these objects is a little bit different, you will see how the accuracy in the borderline regions actually starts failing. So what do we talk about meaningful uncertainties? When we talk about meaningful uncertainties, I want to show you the top right of the plot on the top right. So you can see that there is a high confidence, very dark color of the probability for some objects that are really badly classified. And you can see this because the classifier actually found a boundary and that's it. It didn't think, I have never seen this object in my training set. I shouldn't be sure that this is a blue object or a red object. So when I talk about, yes, I had this animation to show you exactly what I want. So this overconfident prediction is a problem because you will be absolutely sure with a machine learning algorithm, but it shouldn't. So this is where classification uncertainty comes by. So the uncertainty comes from 0, which is the darker color below, to the yellowish or whitish color, which is high classification uncertainty. What you want is that those objects with overconfident predictions have larger uncertainties. Why? Because they have never been seen in the training set. It's not even in the tail of the distribution. It's like, it's really on the far end of the tail of the distribution. So that's what I talk about classification uncertainty. So how do you get them? Uh, it's what we call epistemic uncertainties. We want to have an ignorance about the model that classified, and to answer that, the machine learning community have Bayesian deep learning. So how does it work? Basically, this what you want is that you have some data X, and you want to obtain a classification Y. And you train your machine learning algorithm usually by optimizing some weights, doing negative log likelihood optimization, and you get the probability. Now, if you want to do a Bayesian neural network, what you do is that instead of that being W single weight, well, it's a matrix, but it's a deterministic weight, you have a distribution of weights, okay? So the good thing is that that will give you a distribution of uncertainties. The bad thing is that the posterior is untractable, which is a huge problem. So you need to do variational inference to actually have a result, which is basically saying, well, I cannot get the posterior, but I can approximate it to something that we call variational distribution. This is the QW theta. And what you minimize is when you train is the distance between that posterior and that approximation that you have. Okay. So there are many different ways of doing this. I have implemented two of them. One is called MC Dropout, from Gal and Gramani, that are in the UK, and the other one is based by Backprop by Meire Fortunato et al., which are in Google. So what's the idea? Instead of getting just one classification probability, now you were gonna get a distribution. So for each time step here, I'm showing the classification probability mean in dark line and the uncertainties of it. Now, this is a different plot from the one before because instead of classifying in two classes, I'm classifying in 5, if I recall correctly. But the idea is that at any point of the classification, you will get an uncertainty linked to this. And we want that it becomes that epistemic uncertainty that we're so keen about. So how do you evaluate that? That's a tricky part because nobody usually does physics analysis with Bayesian neural networks. There are some people that have started doing that with active learning as well, but it's something quite new. So the first thing I said, well, let's try representativity. Let's say you train a model with a simplistic simulation, and then you train another model with a closer simulation to the data. You evaluate it on the data, and let's see if the uncertainties are telling you something. And what we found is that actually the mean of the probability, the distribution, didn't change that much, which means the accuracy didn't change, but the tails, the shape of those distributions were larger when you didn't have a representative training set. So the good thing is that the uncertainties work as we wanted them to work. The bad news is this is not a case-by-case basis. This is an average behavior that we find. So not all classifications have such a large uncertainty as we wish. But we found these for the two models, MC dropout and base by backprop. Now, the other thing I wanted to test was out of distribution events or anomalies. We know that in LSST, for example, we will train with cats and dogs, but we will find a zebra or a giraffe or a hippopotamus in the sky. What will happen then? Will I get this overconfident prediction that the zebra is actually a dog? Or what can I do with this? So, of course, we don't have cats and dogs and zebras, we have light curves. So you have a training set to the left that is a supernova, actually, for example. And then the classification ones I did some things that look like periodical variables, some random stuff. And I wanted to see if the uncertainties were giving something interesting. So I take this random thing, apply the RNN, and what I really want is that it says low probability for any class. But what actually happens is sometimes it tells you that it has an overconfident prediction for a difficult class. And this is what happened with the moon I was showing you. It had a very high probability of being in a blue or in the red, but it should have been in the other one. So we did this with Likers and Supernova, and we found the two behaviors. You can actually mimic this with MNIST. There is appendix in the paper that is showing you with MNIST that this happens, regardless if it's astrophysical or not, the data set. So we found some predictions that were very low for everybody, some high confident predictions, but what we saw is that an average classification uncertainty for all these anomalies, which is great, which means the uncertainties are actually giving you useful information, okay? So this is interesting. The bad part is that depending on which method you use, MC dropout or base by backprop, you may get different sizes of uncertainties, and this is linked to initialization problems and other types of little details. But I think this is promising because we are exploiting an information that we haven't been able to exploit in astronomy with machine learning before. And this is something that I think for LST will be very interesting. And we're already doing it for some current data sets. So that's what I'm doing right now. Well, we think it will be applied. In the dark energy survey, I'm actually applying these Bayesian neural networks right now. And also something I haven't talked about, but if you're interested, we can talk about, is ensemble methods. How do you combine predictions from different algorithms? So that should be this year out, soonish. So this is part of what's going on. So what I wanted to tell you is there are a lot of interesting things. For VRO, we have a bunch of machine learning stuff that is happening right now. I didn't talk about half of it. For example, in Think, we're already testing all the highlighted blue science models, which are machine learning models to classify things in CTF and in the future for LSST that come from random forest, Bayesian neural networks, and isolation, forest, etc. So machine learning is key for LSST. I think it's very exciting to try new methods because this is the moment to think about the next 10 years. LSST will last 10 years, so we shouldn't be like being too conservative. We have time to test things. And the summary is basically this. Machine learning is everywhere, from the dark energy survey for cosmology to exploit the sample and get an order of magnitude more supernova than ever before, to study population, to study cosmology, to study dark energy, to the future where with LSST, we will do amazing things with machine learning. And I hope that Think will be a key for all these new machine learning algorithms. Thank you very much. I wrap it up now for questions if you have some.
Thank you very much. So questions, do you have any question for Anais? Yes, David, please.
Yes, thank you. I have a question on the first part of your talk. Can you use your classification to predict the behavior of light curves in other filters? Say you have filters in the RGV and B band. Can you use that to predict what the behavior will be in another band?
Well, you can, of course you can, because you can train it with the SED model of the supernova, for example. That's completely possible. You can also do something that I have been playing a little bit, that is the behavior in the future, in the sense where is the peak, where will be the maximum light, or things like that. Of course, you can train these machine learning classifiers to do anything you want. The question is, what do you want to do? So if you want to do an extrapolation or an understanding the colors in the future, this will be very limited for the SED model that you have right now of those objects, or the simulations that you have. You can also do other things like Gaussian processes and things like that. There's some machine learning code that is not published yet. It should be published soon by LNQ in UPenn that we have been working on, actually trying to eliminate the filters, the colors in the classification algorithms to make it agnostic of the survey. But yes, of course you can do it. Do you have any like more precise science questions that you were thinking of?
The reason I'm asking is that one of the biases in using type 1a supernovae for, say, measuring the equation of state is that we are observing in the optical from the ground. But of course, at high redshift, those are UV rays frame, right? And we know from the low redshift supernovae that the light curves are very different in the UV and the optical rays frame. So this is my concern, and so I was hoping that this would help mitigating the systematics.
That's a very loaded question. I think the way that we are trying to exploit that, at least in the dark energy survey right now, is we're extending the SALTO model into the UV. So we have new measurements of type 1a supernova in the UV, which have been incorporated, so we can have a better model at high redshift. Because at the end, if we don't have those measurements, we can try to bypass it, but this will bias the sample so much. I think what worries me is not that much that right now, because we have this new extended model. Actually, it got published last week. Georgie Taylor from AU I was leading that. It's sold 2021, I think it's called. What worries me is the intrinsic population of type 1a supernova, because we haven't monitored type 1a supernova in large quantities at high redshift. So the evolution of the population parameters, those colors and those stretch, may change with the redshift, which is normal because it's the evolution of the universe. But our simulations are linked to that. So what we do in cosmology, we usually perturb those models, like change the intrinsic populations, change those colors at high redshift and all that to try to see the impact in W. It's not great, but it's kind of the way it's done right now.
Those are that the variations in these parameters are perhaps very different from the ones we expect, right?
Yes.
So I'm going to have a look at your paper when you say you are agnostic about this sort of survey. That would be extremely interesting. It could be more robust, but perhaps less predictive.
Yes, it's still pretty good predictive. The paper is centered more on high quality light curves, but it also depends on the simulations at the end, and the simulations depend on the SCD. So we haven't tested it if we change which salt model we use, for example, to generate the simulations, but that's an excellent idea. I will talk to Helen about that. But the paper should be out soon. It's already submitted to the journal.
All right, thank you.
No worries.
I had a related question about the time domain. I mean, so you don't predict, you've not studied the prediction of the evolution of the light curves with machine learnings, like to predict the peak or to trigger follow-up observations, stuff like that.
So I cannot put this like that. I actually started doing a peak prediction for supernova, and I implemented it. It's good, but it still has a little bit dispersion. So I haven't finished that study. Because the whole point is already with rates, you can see how fast it's increasing. So type 1a supernova, you kind of know how long it takes to rise. But if you start putting other supernova, like core collapse or weird supernova, it's harder. And that peak prediction gets a little bit sloppier. But yeah, this is something I'm working on. I hope that I could tell you it's perfect, but it's not yet.
I had a more general question about the size of the data for SST. I don't remember the numbers. You said something like 15 terabytes per night or something like that.
Yes.
So I'm sorry for this naive question. I don't know the policy. I mean, is there an idea of just keeping, of keeping all the data, or is the plan to keep all the data, or to filter the interesting information with the science results that you could extract in real time from the telescope and just keep the important science data?
Yeah, so there's different, actually, I'm gonna cheat because this is an image that I masked to show you all the data products of LSST. So you still see
Yeah.
my slides now. So LSST has different data products, which are completely different one from the other. So you have the raw data, which there is a copy kept, of course. Then you have the difference image analysis where the alert stream comes from, which is public. So this is public, this part here. And then you have, in 24 hours, you have a database that people with data rights can access with more information. And then you have releases, data releases. So there will be an annual data release, and then there will be a final 10-year data release, which means all data is public. Now, the problem with LSST is because of a big data volume, you can try to get all the images, but how do you get your science out? And when the idea is when science results come out, you can link them to the annual release for some data. But that's stuff that hasn't been implemented yet, of course, because we don't have data yet. So yes, you will have access to the data, but how do you find your needle in the haystack? I think that's a challenge. And that's why, for example, we are making so much emphasis with this broker business, because you can put your computer to receive all those alerts, but your computer, one, will die because of the volume, and two, how do you get the interesting stuff from there?
Yeah, sure.
Yeah.
I had another question about the active learning.
Yeah, sure.
So I'm not sure I understood the loop. You said you would go back to the telescope. So didn't this step will slow down the process of learning and identification?
So what will happen is by batches, basically. So you will have, for example, tonight, we will have a trained model. So the first two-part label pool and machine learning model are already done. And then you will evaluate everything that is in the sky right now. And the evaluation metric will be whether this is an interesting thing to classify so you can improve the training set. And then you can receive that. We have APIs and we have ways of communicating like a stream saying, look, these are all the objects we think could be interesting to follow up. Then once these are follow up, this takes some days, you will update the machine learning model. And that way and that way. This is a completely different thing from following up for the science only. This is more about how to improve our training sets. Yeah. But yes, this will be done by batch, because if not, if we're waiting and updating all the time, so it won't even be done by night. We're trying to do some projections of how often we should do it. It's not that easy because the data volumes are so large that, and the prioritization needs to be, it depends on the telescope that will follow them up as well. So whether it's foremost or we have been thinking of using the AT, which is the one that we use for OSDES, things like that. But it has to be a large spectroscopic telescope in the south. So, yeah.
And if I can continue, I had a question about the in one of your slides, you describe the Think different projects, and you talk about cross-matching with the CDS catalogs. Can you say a little bit more about that?
Yes, of course. This is the left part of this slide. So we have implemented already all the alerts that come by. First, we have a selection between real bogus, so quality cuts basically to take out the things that don't look like are not transients, most likely. And then every alert from those get cross-matched to the CDS SIMBAD catalog right now. Okay, we use the cross-match service. So everything that is in the catalog gets cross-matched. We find the closest neighbor. So if it's a host galaxy, a known variable star, etc. And that information is already available in Think. We also have another cross-match service, which is with VO events and GCN notices, which are streamed, for example, a footprint of gravitational wave detection or things like that. And we try to cross-match it with the alerts to see if we have something in that area. And we have a third one, which is dynamic catalogs, which for me means if you have a catalog that is not public and we don't know anything from it, you can actually, I can show you actually on the web page. I don't know if, I think I need to change the sharing. Yes, so this is the web page. We have a science portal here. And you can upload a CSV file that you have to search for the data that we have inside. And that can be done through the web page as well. But the CDS is all automatic. So you can actually search the classes that are in CDS, this is TNS, but if you're looking for blue SG, which are stars, which I don't know which ones they are, sorry, my astronomy knowledge is not great. You can actually get all the alerts that have been cross-matched to that SIMBAT type.
So this is just a, this is a cross-match in position, but there is no heuristic about the identification for the source that is associated with the event.
Yes, there is.
Okay.
There is in the sense that, well, we have the liker, so this is the liker here. And for example, let's say this is a variable star, which let's say it is for the time being. You can actually try to fit the data, or we can get a classification. Like usually what we do is, even if you have the SIMBAT cross-match, we run it through all our machine learning models and see which is the most probable class of this object.
Okay, and you get this information right on the, from your tool.
Yeah, well, this one is because it's a star is a star, but you can get, for example, I'm going back because the other day it bugged. You can get, these are our derived classes. So these are early supernova candidates, kilonova candidates. All of these are machine learning models combined with the CDS cross-match and other cross-matches that we do that will tell you this is probably a supernova, or this is probably a kilonova, or microlensing as well. There is a machine learning model for that.
Very nice.
Yeah, so if you're looking for microlensing stuff, there are some candidates there. It's a little bit slow today. But this is CTF data. So this is we're testing it right now with CTF, which works pretty well. No?
Thanks.
No worries.
Is there any more questions? No? Okay, so thank you everybody for attending this seminar. And thank you again, Anais, for coming, and see you next week then.
Nice to be here, and hope to see you soon in real life.
Yes.